Oh, thank you. All right. So let's go ahead and get it underway. Paul will be going ahead and covering the slides. So I'll give it away to you.
Thank you very much, Cody. I'm very happy to be here today with BNC, and I would welcome everybody to this presentation on high-resolution scintillation materials and detectors. I'm Paul Schotanus at Scionix, and I would like to share with you the state-of-the-art of some commercially available high-resolution materials, what they can offer you, and what you should keep in mind when designing sensors around these interesting materials. I'll also briefly address what they can do for you, when you need them, and when you don't need them. Let's go to the presentation. Scintillation detectors are standard tools in great many disciplines. Here is a list of applications that is by far not extensive. Medical, health physics, security, physics, you name it. And all these different applications have different requirements. The energies range from a few KeV for X-ray detection to many hundreds of MeV in high energy physics. The temperatures can range from normally room temperature, sometimes -50 in the Arctic, to 100 to 200 degrees C in exploration in oil and logging, for example. And this is clear that every discipline has its own key performance indicators, which means that the definition of a better scintillator depends very much on the actual application. This is something we should always keep in our mind. Let's go a little to the history of scintillation discovery, scintillator discovery. It's closely correlated with the invention of light detectors. We see since the photomultiplier tube was actually developed in the 1950s, we see a steady development of new scintillators, each with different properties. And around 2000, we see a development of some new generation materials called proportional scintillators or high-resolution scintillators. It started with lanthanum chloride, lanthanum bromide, and these days we have a whole family of so-called high-resolution or proportional crystals we can use building scintillation detectors. Materials like cerium bromide, strontium iodide, CLYC, CLYC, GAGG, and some others. The research was very much focused on finding an improved resolution at 662 keV, and this was pushed by security needs. And this development has led to the discovery of these crystals. And you can ask now, what is a proportional crystal? Well, proportionality is the amount of light per unit energy as a function of the energy of a scintillation material. The classic crystals, this number is by far not constant, it varies a lot. You see in the left graph, it varies even 40%. And this implies that you can never reach an extremely good resolution, what you expect based on statistics. Whereas high-resolution materials like lanthanum bromide or cerium bromide, this ratio is much more constant, deviates less from 1. And this means that with those materials, you can actually achieve resolutions of 3 to 4% at 662 keV. You will hear that I refer often to 662 keV because it's some kind of a golden number. But you should not forget there are many more energies that are important for all those different applications. So what is high resolution? We speak about high resolution, about energy resolution of scintillators. Actually, high purity germanium detectors, which are direct interaction devices, which means that the radiation is not producing light, it produces direct electron hole pairs. The resolution is roughly 2 keV over the entire energy range from keVs to MeVs. And this gives you a superb energy spectrum, like you see here in the middle, very narrow lines superimposed on the compton background. So a high purity germanium detector is a real high resolution device. If you would convert that 2 keV in percent, you will get the following numbers for a germanium detector. And resolution is the top table. Resolution goes from 3% up to, at 1 MeV, a fraction of a percent. And this is quite different from the best what we can achieve with scintillators. There you see numbers between 1.5%, roughly 7% at 60 keV. With resolution, we mean the half of the full absorption photon. So it's clear that germanium detectors are far superior in energy resolution, but the Z is not very high, the density, you need to cool them, and they are quite bulky. So scintillators offer an interesting alternative. So now we have to ask ourselves, what is actually a good energy resolution good for? When do we need it? Well, there are two important answers, and that is if you want to detect gamma lines that are very close together, or gamma lines that are superimposed on a large background. You see here, for example, two spectra. The left spectrum is a spectrum from LBC, lanthanum bromochloride, and the right spectrum is one from a very good sodium iodide crystal. This is barium-133 with the main line in the middle at 356 keV. Their difference, of course, is striking. If you want to separate peaks that are very closely together, a high-resolution scintillator or a high-resolution detector is a great advantage for you. When you want to measure just the intensity of a known source, you don't need high resolution, when you're just counting. Where we need a good separation of peaks is, for example, in radioisotope identifiers, very important tools in security these days. Example is shown here at the bottom. But high resolution is not always the only parameter that is important. Other parameters play a very important role as well. For example, when the resolution approaches, let's say, 3 to 4%, the spectrum stability becomes very important. And we should realize that scintillation detectors, the gain is not constant, it's a function of temperature. Photomultiplier tubes are also devices where the amplification is a function of temperature, and stabilization of a detector, scintillation detector, is by far trivial. It is possible, but the resolution is influence of the spectrum finally is also influenced by the stability of your device. In reality, the difference in performance, identification power, between detectors that have 3 or 4% is really marginal. Now let's look at the other important application where a good resolution is very advantageous. And that is, for example, in prompt neutron gamma analysis, where you're looking at very narrow peaks superimposed on a big background. This spectrum here shows you a logarithmic scale, don't forget that. And we see small peaks superimposed on a continuum. And of course, it's obvious that when those peaks are more narrow, it's much more easy to see them superimposed in this background and to calculate the content of those peaks. We shouldn't forget furthermore that at many MEV energies, the homogeneity response along the crystal will also play a role in the final resolution of a scintillation detector. That I will show you a little further on in some equations. Furthermore, it's a fact that many high-resolution scintillators are quite fast, which means they have a fast decay time of the order of tens of nanoseconds. And this is because many proportional high-resolution crystals, lanthanum bromide, cerium bromide, LBC, are cerium doped. And those cerium emissions are fast. They have decay time of tens of nanoseconds. With this fast decay time, you can achieve good time resolutions, and you can also achieve high count rates if there are no slow components present in the emission. For example, you see to the right here some rise times of scintillators. You see cerium bromide, pure scintillator, very fast rise time. And it allows the fast timing that is needed for some specific applications. So many high-resolution crystals are fast, not all of them. Strontium iodide, for example, is an exception. With these fast crystals, you can do fast timing, but it has nothing to do with energy resolution. The limitation of energy resolution of scintillation materials is governed by the equation below. It's a very important equation. It has 3 terms. The first term is the non-proportionality that I referred to earlier. And this is what you see in the left curve here. The line is the ideal curve based on statistics. This is actually the resolution as a function of the energy. And the dots, you see all the different scintillators that we know these days. And they are all above this line. This means that many scintillators are not proportional. The more close to the line the scintillator is, the better proportional it is. So the first term is non-proportionality in the equation. The second term is the statistics. And statistics mean how many light are you actually detecting from your crystal. The third term, I referred to earlier, is the inhomogeneity of the response along the crystal's length. Because if you make a very long, thin crystal, it's not possible to detect from every part of the crystal the same amount of photons. Now, interesting thing is that new materials, like these new scintillators, implies new challenges. Why is this? I'll show you the equation again. Because this ideal super energy resolution, 3–4% or sometimes even lower, is only achieved under ideal circumstances, where the maximum photoelectron detection is achieved, and the optimum homogeneity, which is terms 1 and 3 in this equation. And this means that the very good resolution of high-resolution crystals is only achieved when you use a special photomultiplier tube with a high quantum efficiency, and the light detection surface, the multiplier tube or silicon PM, should be the same size or larger than the crystal. And of course, your window, because many of those crystals are hygroscopic, should transmit the maximum amount of light, so a suitable special glass or quartz window. With other words, the very good resolution of a scintillation detector using a high-resolution crystal is only achieved under ideal circumstances, and many people forget that. It means that not all crystal readout configurations are possible to get this high-resolution detector. I show you two pictures here. One of it is a big crystal with a hole in the middle to measure something in the core. The other thing is a crystal with a larger size than the photomultiplier. If you would use high-resolution crystals for this configuration, you'll never be able to reach the published values that you see in all the data sheets. So it means that the use of high-resolution scintillator crystals, scintillators, will not always lead to high-resolution detectors, and all other parameters need to be optimized. That's something that often is forgotten. Another interesting phenomenon is that low energies, statistics dominate. The interesting thing is that the light output of some good proportional crystals like cerium bromide or lanthanum bromide, LBC, it slopes down at lower energies. And this means, for example, that the best energy resolution at low energies, 6 keV, is not achieved with the famous high-resolution crystals, but with classic sodium iodide crystals. Interesting is also, in literature, we see a lot of publications of newly developed, novel, high-resolution crystals. And if you read very carefully, you'll see that those crystals are always tested with special photomultiplier tubes, where I earlier referred to. They compare often these numbers of resolution to classic materials, the alkali halides or BTO, where standard photomultiplier tubes are used. This is actually not a real fair comparison. And I would like to bring to your attention that if we would use high quantum efficiency photomultiplier tubes also on standard scintillators, we would get quite different numbers than we read often in the literature. That's the reason I put together this table here. In this table, you see some scintillators like sodium iodide, cesium iodide, BGO, and then the high-resolution crystals, cerium bromide, LBC. You see the resolutions in percent, again at 60 keV and 6x2 keV, and I put it also at 2.6 aggregate. And you see there that with a regular sodium iodide crystal, nothing special, cheapest crystal around, on a good photomultiplier tube, I can achieve easy numbers below 6% full width F max at 6x2 keV. And because statistics is so important and influenced by this quantum efficiency, I see at 60 keV resolutions of 7 to 8%, which is quite stunning. To the right bottom, you see a spectrum of americium, 241. 60 keV is the main emission, and you see a very nice structure in the beginning and some peaks there, which are the 14 and 17 keV actinium lines, 24 line X-ray, and also an escape line from the sodium iodide. And this is something you won't see when you use a regular photomultiplier tube. And there at the left, you see the resolution when I use a good high quantum efficiency photomultiplier tube on a classic sodium iodide crystal. So Regular crystals will benefit from the use of special photomultiplier tubes that we normally only use with high-resolution crystals. Unfortunately, not every photomultiplier tube exists in this high quantum efficiency version, and well, we have to live with that, unfortunately, but it's an interesting observation.
All right, excellent. Quick reminder to expand on what Mia said in the chat. If you are holding on to a question, feel free to post that through, and I will make a note of it and introduce it to Paul at the end of this presentation section. But right now, we're going to go ahead and move on into the next section.
Okay, good, thank you, Cody. The next section, I'd like to give you an overview of where we are with the application of new materials, high-resolution materials. Most people have heard about lanthanum bromide. It is around since 2001, I think. Mature material, it's used quite extensively. Unfortunately, it has a background of lanthanum-138 due to some beta emissions and some gamma lines. This is a disadvantage. You see also some other actinium contamination there. But it's often used. We have these days cerium bromide, and cerium bromide actually is a pure scintillator. There are no slow components in cerium bromide. It has a very fast rise time, so it's very well suitable for fast timing applications. And because it has no slow component, you can do really high count rate spectroscopy, for example, in plasma physics experiments. The interesting thing is that it doesn't contain any lanthanum, which is pure cerium bromide. So we see a very nice background without any beta emissions, almost no gamma lines, and we have been able to reduce the actinium background to a very low level of less than 0.01 counts per second per cc. You see in the middle the background spectrum, and all those peaks you see there are caused by either 511s, a little potassium-40 from the photomultiplier tube, and there is some little radium also from the surroundings and the housing material. Bottom right, you see a very nice energy spectrum. Cerium bromide these days offers us resolutions slightly below 4%. Cerium bromide is used in space applications, for example, where you can looking at potassium-40 lines, plasma physics for the high count rate, positron annihilation lifetime spectroscopy. You can also use it for that because it is so fast. Environmental applications and nuclear physics. As I said, it is an intrinsic scintillator. It's very homogeneous in response, quite fast decay, no slow components, it's radiation hard, slightly higher emission wavelength than lanthanum bromide. At the moment, this material is available from 100 millimeter to about 127. Then we have lanthanum bromochloride, which we abbreviate as LBC. It's actually lanthanum bromide. There's 50% lanthanum chloride in it. The properties are actually similar to lanthanum bromide. Light output is the same. Resolutions are roughly 3% at 662 KeV. We are averagely getting slightly lower numbers. The fast component is about 35 nanoseconds. And unfortunately, of course, it suffers from the same lanthanum 138 background as lanthanum bromide. Here you see some typical energy spectra showing a 3% peak and resolution at 122 KeV, which is around 6%. Next, we have a material called strontium iodide. It's for a change dope with europium. It's quite a slow material, so you have to use a long digital shaping time to achieve the good resolution. Unfortunately, it suffers from a small Stokes shift, and this means that there is some self-absorption in the material, and this actually degrades the resolution a little when the crystal size increases. Regardless of this, it's possible to achieve resolutions of 3 to 3.5% at 662 keV. You see the spectra there at 122 keV. And the material is very bright, which means you can have very good resolutions at low energies. It's furthermore radiopure, there are no contamination in there. And this material actually may find very interesting applications in low background, high resolution spectroscopy. Another proportional high resolution crystal is CLYC, cesium, lithium, yttrium chloride. It contains lithium, and that means we can use it for neutron detection. The light output is quite some less than cerium bromide, about 1/3, which means that the resolution is not as good as cerium bromide. We are getting numbers about 4 to 5%. The neutron peak comes up as a very sharp line around 3.1 and 3.3 MeV. We can do fast neutron spectroscopy with it because of the chlorine-35 interaction. It doesn't contain that much lithium. In that sense, we need about 12.5 millimeter, 12.7, to absorb 90% of all thermal neutrons. It has some slow components, unfortunately. That's the way it is. But we can do also very nice pulse-rate discrimination with CLYC to separate neutrons from gammas. With the currently available digital electronics, this is quite simple. Next, I'd like to conclude with another material that is relatively new. It's called GAGG. This is an oxide crystal. It's also cerium doped. Density is about 6.6 prime per cc. It's quite dense. There's an emission in the yellow. You see here the crystal also looks yellow. It's quite bright. It's proportional. It's not hygroscopic, and it's the first non-hygroscopic high light output scintillation material. It's a very high melting point. It's very hard, like sapphire, and that means it's not really an inexpensive material. It's not used that frequently yet, but you can make very nice small pixels out of it. And with silicon photomultiplier technology, it may find some special applications in matrix elements, for example. We shouldn't forget that I don't think that there is a new scintillator that is the ideal material. There are always some disadvantages. The bottom line is often the cost, and cost is related to growing yield, which means how many chemicals do we have to use in producing actually pieces that we can use for our instruments. The material cost is seldom a real issue. So materials that are difficult to grow, actually, like the cerium bromide or lanthanum bromide or LBC, they will always be more pricey than classic crystals. At the moment, the tuning proportionality is a very hot topic. It's possible by influencing this proportionality curve that I showed you in the very beginning by co-doping materials. There's a lot of R&D effort put in at the moment, and this allows us to improve the resolution slightly more than we have as current not co-doped crystals. We see numbers of cerium bromide closing to 3%, for example. We shouldn't forget that high-resolution crystals are very important and can give us many advantages, but energy resolution is not all that counts. And in not every energy, the high-resolution crystals, as they are known, will give you the actual best result. Also, like I said, we shouldn't forget that all high-resolution crystals will exceed in cost an order of magnitude from classic crystals. And for volume bulk applications, it may be a problem.
There we go.
So I'd like to conclude this short overview with a small summary. And that is that very good energy resolutions can be achieved with scintillators, 3 to 4%. And this can be very useful in applications where we want to do spectroscopy or want to see small peaks on the continuum. If we're just counting radiation in an industrial application, we don't need a high resolution material. We shouldn't forget that if we want to obtain a high resolution detector, we should make special provisions in the design and readout to achieve this high resolution in the final instrument. This means we have to use special light detectors and special configurations. Otherwise, we will not have the expected results. Proportional crystals do not always outperform classic scintillators. It depends very much on the application. It's really crucial you have a good look at your application before deciding what material you actually want to use. On high-resolution materials, the stability of the system becomes more important when the resolution gets better and better. And the number of high-resolution new crystals increases every time. And it makes it very difficult for the users to make a choice. And we'd be happy to assist you and advise you what material actually is the best for your application. You can contact us via our website, send us an email, or the BNC website, which you see at the bottom of this presentation. Thanks.
Excellent. Thank you, Paul. So that goes ahead and just about covers the presentation segment. I hope you found that very elucidating. And now we will be moving on to the Q&A segment. And it seems we do have a couple questions. Paul, the first question I have here is, which of the materials presented here are hygroscopic?
Actually, of the proportional materials, all of them are hygroscopic except GAGG.
Excellent. And following up on GAGG, would you happen to have more on the resolution statistics of that material?
The resolution of GAGG is slightly below 6% with half max when we use a photomultiplier tube. When we use a silicon photomultiplier, the numbers are about similar, and that is because the currently available silicon photomultipliers are actually not optimized for yellow emissions. There's development at the moment to make new silicon PMs with a wavelength sensitivity that's more to the higher wavelengths, but we haven't tested that yet. The light output is quite bright actually from GAGG, so you expect actually a little better numbers, but at the moment, as I said, it's slightly below 6% for 662 KeV. I don't have any other numbers available at the moment.
All right, great. And the next question I have here is from Peter. He is asking about CLYC. Oh, there we go. He says that he notices that some points along the line left of the thermal neutron blob, there is, he's wondering if there's something actually there.
You mean the spectrum in the middle?
Yes, the spectrum.
I think this is, I'm not sure what the spectrum was actually. This is a thermal neutron. I think this is a spectrum. No, this is a spectrum from a Californium source, and because you need quite some material to absorb neutrons, about 12.7 millimeter. You also see the emission lines from Californium. So I think we'll see a gamma spectrum there superimposed on the neutron spectrum. The right line, that's the neutron, the thermal neutron interaction.
Oh, he's referring to the PSD section. Sorry.
Oh, the PSD section.
Yes, yeah, that neutron blob.
The neutron blob, yeah. What's the question about that? There's something below there, something below it.
He's curious along the line left of the thermal neutron blob if there is something there, probably possibly fast neutrons.
I don't know. I should look into that spectrum. If you send an email, we can look at it again. I don't know at the top of my head now.
Okay. Yeah, I definitely think that would be good to follow up in email. Moving on to the next question we have here, Muhammad is wondering which type of scintillation crystal would be effective for studying the low energy X-ray range.
The question then is if this is for a diffractometer application or an X-ray spectroscopy application where you have hundreds of counts per second.
Oh, X-ray spectroscopy.
So it's high count rate application.
I would assume so, yes.
For high counted application, you can use, for example, cerium bromide, which allows you to run the detector at megahertz count rate, and resolution is quite acceptable. It's not as good as sodium iodide, but still in the low energy range, it will be a very nice material, and it allows you to push the count rates up to megahertz level.
Great. The next question I have here is going back to GAGG. I have two questions on it. The first one is the lowest energy that GAGG can record or that you have known it to record.
Look, the lowest energy you can measure with a scintillation detector is extremely low, because if you're using a photomultiplier tube, the noise of the photomultiplier tube is a few photoelectrons. So I always say that the lowest energy actually is more determined by the entrance window of the detector. And in this case, it's not hygroscopic. You can use a milder entrance window as long as it's light tight. So you can look down to a fraction of a keV, I would say.
Okay. And then in the regards of KPIs, what is the best timing resolution that has been obtained for GAGG?
That answer, I don't know. I would have to look in literature. I never tested it myself. I don't know what the best time resolution with GAGG is. I wouldn't know why you would use... GAGG has a fast component, but for real good time resolutions, we use either barium fluoride, which is not proportional, it's not high resolution. It's the best time resolution possible, or we use cerium bromide. With GAGG for fast timing, I've never looked into it. Sorry.
All right. Yeah. Moving back to CLYC, seems to be a lot of GAGG and CLYC curiosity. Dr. Haluk is wondering if the neutrons affect the energy of resolution of the detector due to neutron damage in time. So he's curious if CLYC is susceptible to neutron damage.
Neutron damage. It's a good question. I know there are some studies on the neutron damage or gamma resistivity of CLYC, but I don't remember the numbers at the moment. But I think the material was quite radiation hard, just like all these cerium-doped compounds. Cerium bromide, LBC, they're all radiation hard up to 10,000 gray. And I think this material is not an exception. It's also cerium doped. So I think there is something known in literature, but I have to look it up. And if send an email to me, I can help finding the numbers. In principle, of course, every material damages sooner or later, but these materials, these cerium doped materials, tend to be very radiation hard.
Okay. And transitioning actually to cerium bromide and radiation hardness, would you say that cerium bromide is also low in terms of concern when it comes to neutron damage?
Cerium bromide has been tested with protons and with gamma rays, and we actually see no damage up to extreme high gamma ray fluxes.
Okay, excellent. Looks like that's every question today. The question looks like a bit of conversation is occurring in chat regarding the CLYC neutron blob, the PSD chart. We got something from Stelios. They are asking, what type of scintillator would you propose for in situ environmental measurements?
Yeah, it depends what kind of sensitivity you're looking for. Basically, with cerium bromide, which is a low background material, you can achieve better sensitivity than with a classic scintillator like sodium iodide. But we shouldn't forget what I also said during this presentation, that cerium bromide crystals, especially in the size you need for environmental studies, which is roughly 3 inch by 3 inch, are quite expensive. So a classic sodium iodide crystal actually will usually give you sufficient sensitivity. If you would like to get the very, very best, you can use a cerium bromide crystal, which it has been done, but it has a high price.
Okay, one moment. I'm just opening up an attachment somebody sent. And also, Stelius just clarified natural radioactivity. Was that a factor in your answer there? Or is that...
Yeah, natural radioactivity. Because high-resolution crystals give you a better resolution. The minimum detectable activity is better with high-resolution crystals than with classic materials. But it has its price, especially if you want to have high volumes, high mass of the center.
Okay, excellent. And I actually just received an image from Peter on the question he asked earlier. What he's curious about are the outlier dots along that bottom PSD chart. If you can see them, they're kind of hard to see because it's a small image, but you see those tiny blue dots.
Oh, yeah.
And he's curious what those points are and whether they might be fast neutrons.
Honestly, I have no idea. I don't know.
Yeah.
I don't know.
That's a very good idea.
That's a good question. I was looking at the
That is a
spectrum.
good question. Yeah. But definitely feel free to follow up with us, Peter, using either of the contact information at the end of the presentation.
No problem.
I have another question in the meantime from Muhammad, who is curious about which type of commercial electronics are available to read out a cerium bromide crystal.
Well, these days there are commercially available digital multi-channel analyzers made for 14-pin detectors, and they are very convenient to use. They come with software packages, and there are about 5-6 suppliers worldwide who can provide you these kind of digital bases, like Amitech, Ortec, Mirion, Brightspec, Amptec. There are several companies who can offer you this. Khan has a very nice one. All the software is a little different. So these days, the most simple way to make actually a gamma spectrometer is to buy a regular detector with 14 pins. It can be cerium bromide, high resolution, and then buy with it a digital base with 14 pins that can be equipped either with Ethernet connection or a USB connector. It comes usually with software and actually with a laptop and these two items, so the 14-pin detector for digital MCA and a laptop computer, you have a complete digital spectrum. And these combinations are quickly replacing everything that's based on NIM bins and so on. High voltage is all generated internally. That's very easy.
And to expand slightly, we here at Berkeley Nucleonics are capable of providing an array of multi-channel analyzers for different detector readouts. Moving on, Michael is curious if cerium bromide scintillators detect fast neutrons, and can they be discriminated out using PSD?
Fast neutrons mainly interact with atoms that have about the same mass and density. So they interact, for example, with protons. There are these protons that fast neutrons will interact with the material, but the interaction will be very small. So I would say that cerium bromide is not really a material suitable to use for fast neutron detection. For fast neutrons, we usually use special plastics that can be coupled to digital MCAs to do pulse rate discrimination, like EJ276, or we use materials like still beam, and both those materials, still beam and EJ276, you can do pulse rate discrimination, separating the neutrons for the gammas, the fast neutrons, or we can use a liquid scintillator, and liquid scintillator is very well possible. It has, of course, some disadvantages, that it is a liquid. So for fast scintillation, separation from neutrons and gammas, we always advise a liquid, still beam, or EJ276, and just counting fast neutrons you can do with any organic material like a plastic scintillator.
Excellent. Michael's currently typing another response here. I'll let you know what he adds in a moment. In the meantime, I'm going to go ahead and copy paste this message that was at the top of the chat. It has a Skype group, a roundtable in case anything doesn't get answered, or like Peter's question, we need to follow up later with more information, as well as some YouTube to the previous 7 webinars. Thank you everyone for attending. On Michael's through line, he is he mentioned that's good because he's looking to measure gammas in a fast neutron field. So that would be his current application.
Okay, good.
Oh, looks like got some extra stuff here. Questions have slowed down a little bit. Oh, we have somebody typing. So things have slowed down a little. We'll probably wait for a few more questions, and then we'll probably begin to wrap things up. Again, I just said it a minute ago, but thank you for attending, and I hope this has been very informational. We definitely would like to keep in touch with many of you, so feel free to follow through on Skype or send an email. No matter how small the question is, we're typically happy to answer. Oh, thank you, Oliver. He mentions that it was a very great presentation, Paul.
Oh, thanks.
All right, we have another Another viewer typing. Thank you, Anu. Oh, thank you, Burke. Oh, all right. All right. We have one more question here from Fernando that we can get to. What material is most recommended for a high event rate?
Cerium bromide.
Cerium bromide.
Yeah, because it has no slow components. It has been tested up to 5 megahertz. Of course, your electronics should be able to cope with the high rates, but the material itself, your multiplier tube readout should be, of course, configured to cope with high rates. But the material itself, its afterglow is very slow. Another problem with high intensity radiation is that some materials keep emitting light when the main interaction is gone. So when you excite the material with X-rays, you keep away the X-ray source, there's still light coming out of the crystal. This is what we call afterglow. The cerium bromide has almost no afterglow. It's much smaller than the classic materials, orders of magnitude smaller. So this is also an advantage. So cerium bromide is a very nice material for high count rate spectroscopy experiments.
All right, and then just as a last little bit follow-up, and then we'll go ahead and begin the wrap-up. Fernando is wondering, cerium bromide in comparison to lanthanum bromide, is one or the better?
Cerium bromide is better because there are no slow components. Lanthanum bromide has a little slow components. You see this in one of the curves I showed you, the rise time of the pulses, which is faster with cerium bromide. And for the rest of the question.
Oh no, that was their question. If is cerium bromide versus lanthanum bromide for
I definitely would advise cerium bromide because of the absence of slow components.
Okay, excellent. I think that will just about wrap it up for us. Of course, we are always happy to answer questions directly and consult on behalf of everyone here at Berkeley Nucleonics and Scionix. Thank you very much for attending, and we definitely hope to be in contact with you soon.
Thanks.
Thank you.